So let's do another example with relative velocity. In this video, at the end, I'm going to show you a solution visualized so that it's easier to understand, but that'll be at the end of the video, so make sure you stay to the end. And in the meantime, I'm going to walk you through the solution step by step. So here we have a boat that's pointing south to cross an east-flowing river. The boat can go 12 meters per second in still water, and the current is traveling 7.5 meters per second. What will be the boat's velocity relative to the shore? The first thing that I want to do with this question is draw a couple of vectors so that we can understand, kind of visualize. Even though we don't know much information, we want to visualize what we do know. So we have a boat. We have a boat that's going to be pointing south. So a boat is pointing south, right? So we have our boat that's pointing south. I'm going to draw my axes. So this is north, south, east, west, right? And that's according to the convention we have here. So this is our boat that's pointing 12 meters per second, pointing south at 12 meters per second. That is relative to the water. Then we have the water with a current flowing east, 7.5 meters per second. So we're going to have another vector pointed east at 7.5 meters per second. And we want to know what will be the boat's velocity relative to the shore. So what we're going to be doing is we're going to be adding these two vectors, and we're going to be getting some resultant. We're going to be getting some resultant that shows the velocity of the boat in addition to the velocity of the water to come up with a total velocity of the boat, or in other words, this is going to be a velocity of the boat relative to the ground, whereas this is the velocity of the boat relative to the water. So what we're going to do in step one is we're going to assign our variables. So we always want to come up with some letters here. So I'm gonna have B stand for boat, and I'm gonna have a W stand for water, and I'm gonna have an S stand for the shore. So some more information about the boat. The boat, we know it's going to be moving, and this is our object. So we have a moving object. The water is going to also be moving. The water is our moving median. You could also call this the current, but I'm calling it the water. So is our moving median, that's the water. And then the shore, well, the shore's not moving. The shores are stationary. The shore is what we're choosing to call stationary. So it is kind of our reference point, the point at which all the other movement is going to revolve around. So our shore we establish as being stationary, while the boat and the water are going to be moving. So let's go into step two. Step two, we're going to establish our variables, or establish our vectors, sorry. So let's establish our vectors here. What we want is a velocity of the boat relative to the shore. We want a velocity of the water relative to the shore. And we want a velocity of the boat relative to the water. So this is our velocity of the object relative to the ground. The velocity, this is the object relative to the ground, the median relative to the ground, and the object relative to the median. So let's see what data we're given. Well, the velocity of the boat to the shore, that's completely unknown. We don't know the direction, and we also don't know the speed of this. So we have an unknown magnitude, and the direction also unknown. Now for the velocity of the water relative to the shore, well, we have the current that's traveling 7.5 meters per second east. So the water relative to the shore, 7.5 meters per second in the direction east. And then for the velocity of the boat relative to the water, well, we have a boat that's pointed south and going 12 meters per second. The boat can go 12 meters per second in still water. So imagining that the water was still, the boat relative to the water, so in this case we're saying imagine the water was still, the boat is moving 12 meters per second, 12 meters per second, the direction south. Now let's move on to step 3. We're going to plug in our variables. So we have the equation, the velocity of the object object to ground is equal to the velocity of the median to the ground plus the velocity of the object relative to the ground is equal to the velocity of the object relative to the median plus the velocity of the median relative to the ground. So I want you to notice these variables, the O and then the G. So when we have our object and our ground, when we're adding these two vectors, we want the object first and the ground to be at the end. And this variable, or this letter that's in the middle, is going to be consistent, these two here. So that's how we know we have our equation set up properly. All right, so now in this case, let's write this equation with these variables. So the object to the ground, well, that's our boat to the shore. So we're going to write the velocity of the boat relative to the shore is equal to, and let's do this just from here. So if we have the boat relative to the shore, that means that we're going to need the values that we're going to need to be adding are the boat relative to something plus the velocity of something relative to the shore. Remember the boat, and the shore, and then the other one is going to have to be the same. That's kind of your inside. So the B and the S, these are kind of our two outside variables. Then we're going to have the inside ones. And let's look back up here. Which one was that? Well, that was a W. So we're going to put our W in there. All right, so now we have these two are the same equations. This is kind of our general form. This is our form specific to this problem with the variables that we're using. All right, and now let's plug in these known values. So VBS, we don't know. VWB, 12 meters per second south. 12 meters per second south, plus VWS. VWS was 7.5 meters per second east, plus 7.5 meters per second east. All right. So now we have our equation that we need to solve, and we have two known vectors, and we're trying to find the unknown by adding the two together. So step four is going to be our vector addition. So with our vector addition, this should be familiar. Here we have our east/west coordinate and our north/south coordinate. So with our first vector here, we're going to be looking at this one here. So what is the east and west component? Well, in our first vector, 12 meters per second south, we have no component in the east or west direction, so it's 0. And the north or south direction, it's going to be 12. But remember, because it's south, looking at our sign convention for adding these vectors, south is going to be negative. So in front of the 12, we're going to have a negative. So the direction is negative 12. That's how we write south, is with this negative sign. And then our second vector here, we're going to plug in the components down here. So in the east or west direction, we're going to have 7.5, and that's east, so it's going to be a plus. And then north or south direction, there's no value. And if you want to see other examples where we do need to split up the components and we're using sines and cosines, I'll have other examples on my channel. You'll be able to find those, and I'll have those all in the 2D Kinematics playlist. So now all we have to do is add these values. So 7.5 plus 0, it's 7.5, it's positive. And negative 12 plus 0 is negative 12. And remember, this tells us that we're south, and then our plus tells us that we're in the east over here. If this were negative, we'd know that we're going west. And if this were positive, we'd know we're going north. But negative means south, and positive means east. And I want you to see also that now what we've found here with this vector addition, it's going to be matching what we initially drew over here with these components. We have a component of 12 south and 7.5 east, and that will be our resulting vector that I've drawn in red. So what we want to do now is we want to find the magnitude. We want to find the magnitude r of this resultant vector. So r is the resultant vector, and we want to know what's the magnitude. So let's find that in step 5. Let's find the magnitude. So how do we find the magnitude of this vector? Well, we know this is a right angle. So we have a right angle triangle. We can use the Pythagorean theorem. Knowing these two sides, we can find our final side. So the Pythagorean theorem tells us that r squared is equal to this side length squared plus this side length squared. So 12 squared plus 7.5 squared. Meaning that r, if we bring this square root to the other side of the equation, sorry, this squared to the other side of the equation, it'll become a square root. So it'll become a square root. Now solving for r, I encourage you to follow along with your calculators just to practice this and make sure you're getting the same answers. So r is equal to, we get a final answer of 14.15 meters per second. So that is the magnitude of our vector. So 14.15 meters per second, that's our magnitude. That's the speed. But for velocity, we're also going to need a direction. And we want to know the direction. We want to know this direction here. Because we know this vector here. This vector here is pointed east with a certain angle towards the south. So it's south a certain number of degrees from east. But we want to know how many degrees. We want to know this angle. And to find this angle, well, this one's not in the triangle, so it's going to be a bit tricky. What we're going to do is recognize this Z shape. We recognize when we have a Z shape like this, and we have two angles. These two angles are equivalent. These are equivalent angles. And up here, in case you haven't noticed, this is our Z shape here. So that tells us this angle and this angle are equivalent. So when we find this angle here, we're also going to know this angle. So let's find these angles now. It's going to be our step 6. It's going to be step 6. It's the angle. So let's find the angle. So how are we going to find the angle? We're going to use SOHCAHTOA. We're going to use SOHCAHTOA because once again, we know this is a right angle triangle. So we can use SOHCAHTOA, and the side lengths I'm choosing to use here are going to be from this angle, the opposite, and the adjacent. We do know the hypotenuse, but in this case, I'm going to choose adjacent and opposite. You could by all means use the hypotenuse and use sine or cosine, but I'm going to use the opposite and the adjacent. And because of that, the opposite and the adjacent, we're going to use tan. So we know that tan of theta is equal to opposite over adjacent. I want to make a little bit more room for us here. Just a little bit more room, so we're not getting too squished. Of course, this text wants to follow me. Okay. So that tells us from this line, we can simplify this to isolate. We're going to isolate theta. So that's bringing the tan to the other side as the inverse tan. And I'm just going to plug in these values now. So we have a value for the opposite and the adjacent. The opposite of this angle, the opposite, is 12 meters per second. And then the adjacent to the angle is 7.5 meters per second. So type this into your calculator with me. Make sure your calculator's in degree mode. You should get an answer of 57.99 degrees. and that is our angle. So if we want to write this out in a nice closing statement, that's going to tell us, therefore, the boat's velocity, remember, relative to the shore, is 14, and I'm going to keep it at 14, just 2 significant digits in this case, because that's all we were given in the question. So 14 meters per second in the direction, remember we're in a direction of east and some angle south. That's where we get this resultant vector. Remember, we found this angle, we just found it. And again, I'm going to round this. There's no sense keeping 2 decimal points, so I'm going to round this to 58 degrees south. East 58 degrees south. And that is our final answer. Now, as promised, I'm going to walk you through a visual representation of this solution here. So, as you can see, I've got our solution, boat relative to the shore, 14 meters per second, east 58 degrees south. So I've got these color coded to help you be able to follow along here. Remember, what's important to also note is the direction that the boat is pointed in. So the boat is pointed directly south. But when someone standing on the shore is watching this boat move, so we got a guy standing on the shore and he's watching this boat. He's gonna see this boat move on an angle like this. So it's pointed south because all the power that the boat has is pointed south. But then the water drifts it. The water's got a current that carries it. So if we're just isolating, so imagine we had the boat not moving. The boat was just sitting still. The water would still carry at 7.5 meters per second this way. So our guy on the beach there, even though we in the boat feel like we're sitting still, he's watching us get carried by the water 7.5 meters per second. But when we go 12 meters per second south, that's not the only direction we're going. The water's still acting. So we're going south while the water's pulling us east, and doing that all together in one motion makes us go on this diagonal here. So remember, even though we're not going to be, it's not like we're pointed in this direction. We're not pointed 58 degrees south of east. We're pointed straight south, but the water carries us towards the east. And we're going to keep drifting just like this until we hit the shore or until we change directions. But I hope this solution made sense. I hope it helped. And that is the end of this example.